Welcome to the subject operating systems, the topic page replacement algorithms. The topic page replacement algorithms is because of the idea called virtual memory. There was only main memory which was working with the central processing unit. A good portion of the main memory was taken away by the operating system. Now, the functionalities of the operating systems are increasing. Therefore, the demand on the main memory for the operating system code has increased, leaving very little room for the application programs to be stored in the main memory. The architecture demands that the program written by the user should be in the main memory, the full program must be there in the main memory, the input data must be there in the main memory, the output data that is coming should also be stored in the main memory before anything can happen. That means, there is a tussle between the operating system and the user. Now, in the process what we understood after serious study of systems, how application programs are written, we understood that there is definitely reason to believe that because of the fact that input and output devices are very slow in comparison to the central processing unit, most of the time the application program is only talking to the operating system to work with the input output devices. Very small portion is what is called CPU burst, which is happening in the CPU. This is how we have analyzed many programs, many application programs that have been written. Let us imagine that is only one application program in the main memory. A huge chunk is taken away by the operating system. The code for the application program will become very small. Input data must be there, output data must be there. We are taking away lot of memory for various other activities, and the complexity of the application program is thus dictated by the available memory size. Whereas, the application programmers are becoming more and more demanding, they want to write more and more code, they want to address more and more complex problems. So, there is another reason why we thought that the existing main memory size is severely challenged. However, the concern here is that the central processing unit is the most expensive component and the CPU burst of any given application program is very small. Most of the time, however complex the application is, it is only using the operating system to talk to the input output devices, very little time of the CPU is being used. If lot of money has spent on the CPU, such small utilization of the CPU means that the resources are completely underutilized or most of the time unutilized. Therefore, the concern came as to how do we improve the CPU utilization. If one memory is there, let us suppose it takes 3 hours to execute, out of which 2.5 hours is being spent only for the input output exercise, the processing is only for half an hour. What is the utilization? The utilization is just 1/6 of the on time of the CPU. 1/6 is a very small utilization, it is just around 14 to 15%, maybe it is 16%, 16 plus percent. That is how it is being utilized. So, therefore, the very low utilization of the most expensive component called central processing unit. What is the solution? One solution that came about very early in the design of operating system is to talk about an idea called multi-programming. There is no need to believe that only one application program can be in the main memory. You can have one more application program in a manner where the operating system which is already in the main memory becomes very alert. When one application program is talking to the input and output devices, it automatically switches to the second application program which is already ready there in the main memory and it takes it to the CPU. Which means that already one application program is fighting with the designer saying that your OS code has occupied so much of main memory, giving only this much main memory for me. Into this you are asking them to make it little more shorter, please accommodate one more application program in the same main memory, so that we will increase the CPU utilization. What was happening is the idea is good, but then whatever be the application programs that were being written at that point in time, maybe 50 years back, we found out that any beyond 5 application programs in a multi-programming mode is going to be counterproductive. Instead of switching between operating system and application program, now we are switching between application programs and operating systems. So, 3 programs is good, 3 to 5 becomes very challenging. After 5, this idea is becoming more and more complex in terms of shuttling between the various programs, operating system, fighting over for that memory space. Multi-programming was a good idea, but then it was not yielding desired results any beyond 5 jobs. Well, the point is, computing was not so popular from day one. People were very reluctant to take to computing. However, as computing as an idea, as programming became more and more challenging, intellectually stimulating to attract brilliant minds, a lot of people began to use this machine called computing to get their solutions expressed in a manner where they are machinizable. They can simply go ahead and machinize that. This is what was happening, and more people were coming to the machine. So, what we said was, multi-programming is not such a good idea, because 5 application programs simultaneously in the main memory and the operating system doing the shuffling, more time will be spent on shuffling rather than going to the CPU. Therefore, what is the other idea? The other idea is multitasking, which means that there should be more application programs. However, it is not because the application program is asking for some input or output that the CPU or the OS is getting into the other application program. There must be some other criteria. What is that criteria? The criteria can be the scheduler. The CPU will now get scheduled based on certain characteristics of the way in which the CPU scheduler is working, but that is an exercise which is the functionality of the CPU. Is there some other related aspect that can happen in the main memory is the next question. If something is happening in the main memory, what can it be? We said that there is no need for the entire application program to be there in the main memory, because at any given point in time only a few instructions are necessary, because the CPU is already scheduling. Depending on what the CPU scheduler does, it expects one application program to go, then why should the entire application program be there? If the CPU decides that program 1 is executing for some time, for 1 second, it will execute. After that, whatever is that program doing, the CPU will go to the next program, P2, program P2, P3, P4, P5, then why should we occupy the memory with the full program? This is the genesis for the idea called paging. So, we came to a conclusion after a lot of study, after a lot of experimentation, we came to the conclusion that there is no need to keep the entire application program in the main memory. A few chunks, which are called pages, of every given program may be used as a representation of the program in the main memory. Now, within the available main memory, we can have many programs whose footprints are the number of pages. It can be there. Now, what happens if the CPU wants a particular page depending on the execution and the page is not there? It is called page fault. What is the guarantee that whenever the page is asked, it is there in the main memory? We said we do more studies, we come up with what is called a working set. That is, this page is currently to be executed, some pages before this page, some pages after this page will become a working set, they will be there in the main memory. How to decide how many number of pages will be there in the working set? These are the design constraints, they are conflicting, but what we should understand is this entire exercise must be in tandem with the increased functionality of the CPU scheduler, which is becoming more and more robust, more and more sophisticated, to make sure that in addition to CPU utilization, it should minimize the waiting time, maximize the response time, more number of jobs must be executed in a given time, throughput. Overall, the user satisfaction must be high. It is not merely a CPU utilization, a single figure of merit that we are talking about. We are talking about at least 5 metrics that we must satisfy. So, what we need to understand here is that when the page is asked, we should have a very quick mechanism by which we should be able to get that page, otherwise it will be a page fault. On a page fault, depends on how the CPU is scheduling. It can go to another program, it can say that there is something wrong, we can do some other exercise. However, the idea of page is very simple. The entire program is divided into a set of pages, each of specified page size. How will we decide the page size? Again a design issue. If it is too small a page size, very frequently we have to run around from the secondary memory to the main memory, because only a footprint, hardly 10 pages are there, other 1000 pages of the program are in the secondary memory. So, we will be shuttling between the main memory and the secondary memory. Once again we talk about something that has to move out of the execution space. It is the secondary memory, nothing can happen. If it is too small a page size, we talk about this kind of an exercise. If it is too large a page size, what will happen? The entire purpose is defeated. One single program will occupy the entire main memory, most of the main memory, leaving little scope for the other programs to come. This is what was happening in the other idea called segmentation. Paging was one idea which was very popular in virtual memory. Segmentation is a second idea. I have already mentioned the paging considerations, the page size, the number of pages called working set, everything should be there. What is the tolerable page fault? What is the way in which the CPU scheduler recognizes the page, which page should be called, how to deal with page fault, those will be the topics. Segmentation, what it does is it divides the entire program based on a function or a set of functions. It makes business sense because once you start executing a function, it is expected that the entire function is executed and then it goes to the main routine. The very programming flow is based on subroutines and functions. Imagine the entire function is a segment and it is there in the main memory. Segmentation is also done in many cases. What we need to understand is when you become functional based, either you have to roll out the entire function or keep that entire function in. We use a technique called swapping. Even in paging we use a swapping, but swapping is more popular in segmentation. I will tell you one good example. In the operating systems domain, if it is occupying too much of space, like in MS-DOS early days, internal commands, external commands. Internal commands are already loaded into the main memory at the time of booting, when the system boots. External commands are brought in only when there is a call. Where will the external command find space? It has to overlay. It has to remove the internal commands and the external command should overlay. This takes time. We need to use a better method called swapping. We need to swap the page, I understand, we need to swap the segments, but swapping is a more expensive exercise than simply talking about page and page replacement. The idea of page replacement caught on because it is very elegant. The number of pages, the paging consideration is very simple. What should be the page size? Optimal page size, optimal working set. What should be the page replacement policy? When a page fault occurs, what should the operating system do? And when it is all over, how to clean up the pages? The pages can be anywhere. The concern here is that in segmentation, if the program has completed execution, that segment is doing nothing. In the case of segmentation, it becomes very difficult to make room for the occupied memory and the free memory. It is lot more simple to do it in page. This is one of the core reasons why segmentation has not become so much popular in the virtual memory management. Paging has become very popular. So, this is one of the policies. If you want to use segmentation, please be prepared that it becomes difficult to do compaction. Compaction takes time. We need to also do garbage collection, that takes time. A lot of precious CPU time will go away in terms of putting all free memory in one side, all occupied memory in one side. It can be done, but it takes time. What was our goal? We need to now have a 5-pronged metric system: CPU utilization, minimized waiting time, increased response time, very quickly it responds, increased throughput, not merely these, but also work should be done. more programs should be executed within a given time, virtual memory policies. We have all these ideas being spoken of into the virtual memory. So, the main memory size is limited, but because of a huge secondary storage, we get a feeling that using paging or segmentation, whichever policy you have, these are the drawbacks, these are the pluses. It gives an impression that every application program has virtually infinite memory on hand, which only a footprint of that application program, working set based on a page size and the page replacement algorithms is all that is happening. What are the goals? Want lowest page fault rate. Evaluate algorithm by running it on a particular string of memory references. A default, you can generate a random sequence of the page numbers that may be called. You can do an analysis offline saying that this is how it happens, page faults, page replacement on that string. In all our examples, we use few recurring reference strings. Graph of page faults versus the number of frames. So, we have, let us suppose that if you have one frame, only one frame in the main memory, what is the number of page faults? 15 page faults. Each time one memory location is there, it is asking for where is that memory location, not in the memory, so you get it. It is something like that. If you have 2 frames, the number of page faults decreases. If you have 3 frames, it will come down to this much, 4, 5 frames. But as we keep telling, the switching time between the way in which we talk about number of frames together, how many number of frames? Working set. Frame is a very generic idea. You can fill it with the set of working set or a segment or whatever it is. So, if the more the number of frames, the page fault should decrease automatically. The idea is very simple, but in practice we have a different experience which we will see different outcomes. Treats page frames allotted to a process as a circular buffer. When the buffer is full, the oldest page is replaced. So, there is a system support that is necessary that tells that this came first, this came later. So, this page should be put in first. There are a lot of requests, lot of footprints of many process application programs are there in the main memory. If this is executed first, it should go immediately to the next. The page fault has occurred, a page is already waiting to be put into the main memory, and how do we track the waiting pages to be put into the main memory? Waiting pages, waiting segments, ideally it should be first in, first out. So, let us see how it looks like. This is a reference string, page number 7, page number 0, page number 1, page number 2. These are the frames that it is expected. Initially, there are only 3 page frames. Our system of virtual memory can manage only 3 page frames. Initially 7 was there, second the request for 0 to come in, it came, 1 came in, now it wants 2, where will you put it? There are only 3 page frames, where will this 2 go? So, what we do is, which was the first page that came in? 7, throw it out, put 2. Then what is the page that is requested? 0, it is already there. Then what is the page that is requested? 3, what came first? 3 came, 0 was already there, you throw away 0, put 1. So, if you keep on looking at it, what is the idea that we are talking about? For the given reference string, in the first in first out algorithm with 3 pages only, and what we got is 9 page faults. With 4 frames, you are getting 10 page faults. So, please understand that it is not a linear progression. 3 frames and 4 frames is not going to make such a significant difference on the page faults. Why? Because we do not know the sequence of frames demanded by the application program. On an average, if this is the reference string 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5, if it is 3 frames, you get 9 page faults. That means 9 times the CPU has demanded a page, it is not there in the set of frames, it has to wait, it has to go to the secondary memory and get it. If it is 4 frames, it is not a dramatic increase, it is just 10 page faults. So, this is what we called is Belady's anomaly. It does not mean that if you have large number of frames, the page faults will come down significantly. As a matter of fact, when we were doing this exercise with multi-programming, as I said earlier, beyond 5 programs it was called thrashing, a phenomena where the operating system is only boxing within the main memory and the secondary memory. It is nothing to do with the CPU. This page is there, that page is there, immediately it will have to replace it. This is what is called Belady's anomaly. The illustration is very simple. We talked about the number of frames, and it is not dramatically increasing beyond 5 frames for a given particular string. It is saturated. You do not get any improvement. So, we should know that there is no need to think that we should always have a huge stack of frames. It is enough if we have frames, the number of frames that can accommodate the working set. So, as the number of frames increases, there is a saturation point which is there. Lot of system studies have happened. Beyond this you do not get any improvement. So, why do not we stop with 5 frames? For typical operating system, we tell that we track 5 frames waiting, and then we introduce an algorithm. In this case it is first in first out. The optimal page replacement policy selects for replacement of the page that will not be used for the longest period of time. The page is already there in the frame, but the CPU is not calling for that page. We know how to track it. For a lot of time it was not used. So, optimal page replacement strategy, see the number 7, it has not been used at all until now. Number 7 is easily removed. Only once it happened here, only once it has happened here. So, it has not been used for a huge series of exercise. So, the number 7 is already out. If you remove that number 7, you can be very happy that you can persist with the existing pages and then go ahead. The OPR is nice, but please remember all these things are statistical analysis. For the same reference string, if you look at it, the same reference string as we used for the first in first out algorithm 1 2 3 4 1 2 5 1 2 3 4 5, which with 3 frames we got 9 page faults, with 4 frames we got 10 page faults. Now, with the optimal page replacement for the same string, for the 4 frames example, we got 6 page faults. So, by changing the page replacement algorithm, we were able to reduce the number of page faults from 10 to 6. However, this is not a solution for all possible things. For a given reference string, this is the result. So, if you want to use first in first out, we got 10 page faults. If we use optimal page replacement, we got 6 page faults. What is the guarantee that each time you see this kind of a sequence? There is no guarantee. We have studied lot of programs and we know that one page replacement algorithm that is good is first in first out. The second one, which works in many cases, is optimal page replacement. What are the other page replacement algorithms which we have been talking about? So, the other page replacement algorithm, least recently used policy, replaces the page that has not been referenced for the longest time by the principle of locality. There is a working set. The working set is determined by using a principle of locality, which says that again lot of studies have happened on a given program. If a program is executing this particular instruction, some n number of instructions before and n number of instructions later are most likely to be referred by the program. Lot of programs have been studied, application programs, and we arrived at this idea called principle of locality, which will allow us to determine what is the working set. Performs nearly as well as the optimal policy, but then we are not really looking at optimizing, making sure that it is indeed that. So, LRU will keep on doing that exercise. It can happen with a given page string. A least recently used algorithm with 4 frames in the stack generates 8 page faults for the same reference string. So, what is the difference? FIFO generated 10, the optimal page replacement generated 6, the least recently used generated 8. What we think is that the least recently used algorithm is what averages out well across multiple programs, even though the optimal is very attractive, it gives only 6 page faults, we have to minimize the page faults, 6 page faults, it is very expensive to implement. So, we started using what we called the least recently used more frequently than FIFO. It gives a reasonable midway between first in first out and optimal. Optimal is more expensive than least recently used. Now, this entire idea is called demand paging. The virtual memory manager is only waiting for a trigger from the CPU scheduler. Only if the CPU scheduler wants, we will go ahead. If it does not want, it does not bother about the page. We only need to talk about what is happening with the way in which the CPU is executing and nothing else. Whereas, there is another page replacement policy which is called anticipatory paging, where the virtual memory manager is a little more expensive, lot more expensive. It keeps studying the pattern in which the program instructions and the data is being used, and it anticipates that this particular execution will want this many pages. This would require expensive hardware and a great deal of overhead. Even the LRU, which is demand paging, has an overhead, expensive. Anticipatory is much more expensive and a great deal of overhead. So, what are we doing? We are using certain simple implementations. There is a counter implementation. How do we implement an LRU? There is a counter, there is a stack. A counter will keep track of how many frames are used, and a stack will keep track of what are the frames that are being used. The implementation is easy, but then if it is implemented in software, it is going to take so much time. How much of hardware support can we give? There are systems which have built a better hardware. Now, the concern here is that the operating system should be generic enough. It should not be tied to a particular hardware. For example, we had a wonderfully designed IBM PS2. The OS2 was designed specifically for PS2. It is an operating system well designed specifically that works on PS2. If the PS2 did not succeed, OS2 will not succeed. It is so tailor made to the architecture. So, we have been saying that hardware architecture is like this, the hardware is like this, the OS is like this, the application programs will be written like this. Maximum business wise success happened when the hardware architecture is stable, it is like this, OS is stable and is portable. Put together, people have been using application. Very rarely, if the hardware and the OS are made for each other, it is not succeeding. Unix showed us the way. Unix and C are made for each other. Unix is portable across many hardware platforms. The success of Unix is a great lesson in itself, and what we have done is use this stack implementation, use a simple counter. It is very easy to implement. Always take the bottom one, it goes. Now, this is how the number of pages, page references, you can have a simple matrix. Matrix is a data structure that is so easy to implement in all operating systems, and the pages are referenced in this order. This is a reference string. You simply use a matrix and automatically the page replacement algorithm will tell you which pages of what program are there in the main memory, how to replace. Reference bit. With each page associated a bit initial to 0. When page is referenced, it is set to 1. Replace the 1 which is 0 if 1 exists. We do not know the real order of use, however. It is a very simple idea. Very quickly, all pages where the reference bit is 0 are liable to be taken away. Only those where the reference bit is 1 will remain in the main memory. It is an approximation of what we are doing. It is possible that what was 0 1 second back is needed the next second, but at the time when we were shuffling the pages, the one that was marked 0 was moved out. Then there is a reference byte. Idea is to record reference bits at regular intervals. Keep a byte of reference bit so that you know how to measure. When was it shipped out? When was it shipped in? When was it not necessary? When is it necessary? But then it occupies more time in your, more space in the data structure and more time for the CPU to process. Please understand that memory is passive. No execution happens in the memory. The CPU will need to do this exercise for us. That takes away more time. So, in addition to the OS demanding more and more space in the main memory, limited main memory, it is now demanding more and more CPU time. There is no excuse, because that much of time spent for operating system will help you do better programming. In many ways, operating system can be perceived as a necessary evil. It eats away some memory, it demands the CPU time, but overall it is very nicely designed with conflicting demands, contrasting ideas, contrasting functionalities, ever increasing number of functionalities. It is able to give you minimum waiting time, maximum response time, high CPU utilization, high throughput, and overall user satisfaction. These remain the cornerstones of the performance indicator of your operating system, so it is worth investing. It is true that the operating system will demand a bit of your main memory, limiting memory for application programs. It will also demand the CPU involvement in doing this much of exercise. Where is there, if nothing happens in the memory, the CPU will have to switch to the operating system, find out which are the pages that are marked 0, throw them away. If you have a reference byte, the CPU will be able to find out how frequently this page has gone out and come back. You can have some metrics based on it. So, we have a way of talking about how to recognize which is the optimal page to be replaced. There is a clock in that, the sequence is there, frequently thrown out, frequently brought in. So, we know how to have an optimal page replacement, how to have a least replacement. The clock, the set of frames candidate for replacement, is considered as a circular buffer. When a page is replaced, a pointer is set to point to the next frame in the buffer. A reference bit for each frame is set to 1. When it is time to replace a page, the first frame encountered with a reference bit set to 0 is replaced. Then it comes back. During the search for replacement, each reference bit set to 1 is changed to 0. So, this is how we have been talking about. We said that wherever you find a 0 in the reference bit, just it's a candidate, the page candidate is marked for throwing away. Suddenly, if you need again, you bring it back. It may be true that we find that most demand pages have already gone out, but it is a compromise, it is an engineering compromise. We need to make sure that the entire exercise, all functionalities of operating systems are working in tandem. There is a clock page replacement algorithm, circular queue of pages. This is how it is. At each tick, clock based, time bound, you go ahead and replace. That is another algorithm. So, we have seen 4 page replacement algorithms: first in, first out, optimal page replacement, least recently used, then there is a clock. At every time when you are going through this circle, wherever you see 0, just go ahead and replace. The next as you come back, it will change the code, the next victim will be 1, the reference bits will be 1, the next we can always say that this page will go away. There is another example, different policies. We can think of many page replacement algorithms, but what is the crux? Please remember that we need to go back and find out that we have certain goals here. The goals of page replacement: we want the lowest page fault rate. Evaluate algorithm by running it on a particular string of memory references. We use few recurring reference strings. So, this is how we have been building the entire set of page replacement algorithms, and what we found is that using a simple data structure, limited hardware support, we are capable of showing that 4 different algorithms can be easily compared, and this is what it is we have been doing. And what we have ended up is a comparison between clock with FIFO and LRU, first in first out, and LRU. This is what we saw last, page address stream. Now, you see the number of page faults remains a great metric. It is true that you can always change the reference string and get different results. We are not in a position to anticipate what will be the stream of pages that will be called by any given set of application programs. So, we have to study, improvise. In the world of commercial operating systems, we do not have any control. It is like this. For the environment in which the machine is working, you will get this kind of a performance on the page replacement. There are many factors, 18-20 functionalities. Today, a general purpose operating system fits well in many environments. Some functionality is taking a beating, some other functionality is getting a fillip, some other functionality is shining bright. It happens because all functionalities, 18 to 20 functionalities of operating systems have conflicting demands, varying degrees in which the compromises are made by the OS designer. Whereas, we need to understand that on an average certain implementations have withstood the test of time, and therefore we tick LRU. Normally we say LRU is a replacement strategy, we will go ahead with that. Numerical experiments tend to show that performance of clock is close to that of LRU, but then anything that is dependent on clock we are a little bit wary, because clock is something which is very precious. We use multiple clocks, then the concern which clock to use. The bigger concern, it is something which is completely linked to the control unit where the clock comes. That is what I was telling at the beginning. The clock pulses are generated in the control unit. We do not want to tie it to the control unit, we would want to tie it to the CPU scheduler. So, experiments have been performed and the number of frames allotted to each process is fixed, and when pages local to the page fault process are concerned for replacement, when few 6 to 8 frames are allotted per process, there is almost a factor of 2 of page faults between LRU and FIFO. LRU scores by double the factor. 6 to 8 frames, LRU overall is giving a very good performance over a span of time, over a variety of application programs. This is a very great study, lot of things have been implemented using this. So, this is how it works. LRU is very steady. Please remember that as you get more number of frames allotted at 14, you will still get a steady LRU. Here we get FIFO is giving maximum. These are the page faults for 1000 references, 1000 references. FIFO is very high, always higher, and this is over a large number of programs, 1000 references. String is not merely 10 or 15 as I have used in the references, a reference string, it is 1000 long string, and the number of faults for FIFO are very high. Even at 14, clock is still high. LRU is like this. Optimal algorithm is very attractive. It always gives theoretically that is much better than LRU, but then implementing optimal is going to be very costly. LRU uses simple data structures which can be implemented either in software or hardware. By implementing in hardware, it is not going to be prohibitively expensive. Please understand that anything to deal with hardware, $1 increase in one component can manifest as $100 increase in the overall product. Hardware implementations are like that, very expensive. If it is demanding too much of hardware, the overall product becomes very expensive. Today computer is more or less a consumer good. Mobile phones have so much of computation. The existing architecture, we do not have the luxury to build so much of hardware. Anything in hardware can also be done in software and vice versa. Hardware is fixed. When it is done in multiple components, the price will come down, but then it is still higher. Every $1 increase will manifest as $100. It is not flexible. Hardware is not flexible. Today we are not making a serious distinction between hardware and software at step 1. They are all co-designed. At a later stage, it can be decided what is implemented in hardware, what is implemented in software. There is no need to talk about it right up front. Methods have changed, hardware, software, co-design has come. So, what we have done therefore is utilize this idea that LRU appears to be the most popular, very reasonably implemented method for page replacement. LRU is least recently used. In this particular lecture, I have compared 4: first in first out, clock replacement, LRU, this optimal page replacement. Now, please understand FIFO is always showing more number of page faults. Clock also shows page faults. What was our goal? Minimize the number of page faults. Number of frames, even if it is 16, it reaches a summit. We should understand that by definition it is like that. We have to be very careful in noting that the number of page faults reaches a summit. It is not that we increase the number of pages and then it goes on increasing. Let me locate that slide where we see that it will reach an average. The number of page faults always do not show the decline. in the way it is being implemented with maximum number of frames. That is how we will have to look at it. You see this, we think in theory that had we had more number of frames, I would have brought the number of page faults down drastically. It does not happen like that. So, in all these cases, comparing over 4 page replacement strategies, we see that it is absolutely important that increasing the number of frames alone is not the solution. Toying around with the page parameters is not the solution. Eventually, what dictates is the actual reference string that is generated by the application programs that are sharing the main memory and demanding the CPU. In all these cases, over years, LRU is found to be very attractive. Most of the operating systems which are using LRU tend to show good benchmarking results. LRU has been dictating many purchase decisions as to what is the software, what is the hardware. Counting based algorithms keep a counter of the number of references that have been made to each topic. 2 possibilities: least, most recently used. Least replaces page with smallest count, that is frequently. F is for frequently. There are other algorithms, you can create more. Least frequently used, most frequent, why only FIFO, why only clock, why only LRU, why only the optimal. We can use least frequently used, we can use most frequently used algorithm. There are so many such algorithms. Now, into this, it is not the simple case of coming up with yet another page replacement algorithm, but the implementation details are absolutely necessary. There is no need for a page that is marked 0 to be directly shunted out of the main memory. When it is required, we will bring back. You can have a buffer, you can keep it in between the secondary memory and the main memory. The buffer usage of buffer, multi-level hierarchy of memories, has proven to be very useful in operating systems. How many buffers? There is a cache memory, there is a secondary memory, there is a main memory or primary memory, how many levels in between. This becomes a bigger challenge, and it is much better that we use LRU, which is most popular, and then create some facility for having a buffer in between. 2 lists of pointers are maintained, each entry points to the frame selected. So, the point is, we will decide how many pages can be buffered. They are not taken away and put into the secondary memory. Accessing secondary memory, working with secondary memory is much slower than what we are doing with the main memory, but then we can't have so much of main memory was the thinking at that time. Today we are relaxed on it. Main memory is not so expensive. At low cost, we get a huge memory size. The cache memory is relatively faster than the secondary memory, but not exactly the main memory. We will keep certain things in the cache. How many levels of cache? This is what we call levels of memory or memory hierarchy. We should have more concerns about cache coherence, cache consistency. Cache memory management in itself is a very good topic, very challenging topic, which involves many factors. At each page fault, the 2 lists are first examined to see if the needed page is still in the main memory. So, if you use one cache memory, there are a set of pages which are in the main memory, there is a set of pages in the cache memory. First you check in the main memory. If it is not there, check in the cache memory. If it is there, you bring it back, it will be faster. If it is not there in the cache memory, you have to go to the secondary memory and bring it back. Cache is useful, but then you have one more data structure. When all the pages are reshuffled, pages are modified, pages are shunted in and out of the main memory, then what remains? Some pages are over, they are no more needed. Some pages are existing, but all spread over. So, we said there is a need to collect all pages, completely clean up, memory purged, where the pages are not like the program has executed, is over. So, what is remaining should be cleaned properly. We should have a way of making sure that the demand cleaning when it is necessary, memory compaction and memory deallocation, all those things, the garbage collection, memory compaction, these routines will have to happen, and what we need to understand is it can be done a priori, or when lot of pages are demanding, the operating system can wake up, let us clean up certain things, and then it goes. That can also be demand, or it can be every 10 minutes you purge a few pages. You decide If the operating system is in such good demand, it will happen like that. A good compromise, not all dirty pages are written out, but only those chosen for replacement. Writing is done in batch. How do you write it? Wait until all a batch processing cache and secondary memory is much more attractive and positive. Thank you very much.